Good morning. A few things that I want to add to last week's lecture on DC circuits. DC stands for direct current, while AC stands for alternating current. Well, last week we talked about DC circuits, where the current does not change direction, that it's constant once you get it going in a circuit. AC, alternating current, is the second part of the lab for this week. For the circuits, whether we're talking DC or AC, but for the DC circuits, we had potentiometers, and a few people have asked me about the potentiometers. The potentiometers are variable resistors. They're these little tiny blue boxes, and they're labeled with a resistor value. So, for example, a 5K potentiometer or a 5,000 ohm potentiometer, right? The 5K potentiometer has 5K resistance between the two outside legs. So let me try to draw on this picture. But we've got a resistance on these two outside legs inside the little blue box of 5,000 ohms, and that's not going to change. But the third leg will have a variable resistance when we turn the little screw on top, right? That little yellow screw on top. So you're going to find a little screwdriver or something that you can stick in that screw and you turn it. And if you measure the resistance with your multimeter between these two legs, it's always going to be 5,000 ohms. But if you measure the resistance between these two legs, right, it's going to be somewhere between 0 and 5,000 ohms. And then you might be able to guess that if you measure the resistance between the other two legs, or the third leg and the middle leg, then it's going to be the opposite. So if, for example, I don't know if that was obvious what I just did, but let's just call this leg 1, and the other, the middle leg, leg 2, and the third leg 3. The resistance between R13 is always 5,000 ohms. The resistance between R12 is variable from 0 to 5,000, so that the resistance from R23 is variable from 5,000 to 0. In other words, the resistance between 1 and 2 plus the resistance between 2 and 3 equals 5,000 ohms. So as one goes up, the other goes down. So you can use either pair of legs, 1 and 2, or 2 and 3, as your variable resistor. That's all you need to know in order to use one of these variable resistors. The other thing that I wanted to review from last week is we talked about circuit diagrams. In a circuit diagram, you've got a battery. Well, I mean, in the kind of circuit diagrams we're drawing, you've got a battery, you might have a resistor, you might even have a capacitor, and we're going to add things like, later on we're going to add all kinds of things, diodes and what are they called? Op amps and other kinds of chips. But let's just take a simple resistor, a simple circuit, like a DC battery with a resistor and a capacitor. So this would be a potential difference, this would be a resistance, this would be a capacitance. Now, if we wanted a variable power supply for an AC power supply, we would put in a variable power supply, which can be drawn that way, and there's a resistor, and there's a capacitor, and that's an RC circuit. I don't know, I mean... I know. If you want to put in a digital multimeter, right, let's add I don't know why I changed color. Let's add a digital multimeter. We want to measure the voltage across a resistor. Here's measuring the voltage across a resistor. We go on to measure the voltage across a capacitor. Here's measuring the voltage across a capacitor. So when you want to measure potential differences, it's a difference between 2 points. So you want to take your digital multimeter, put it in the voltage setting, and put it across the thing that we want to measure the voltage across. Hopefully that you remembered from Physics 116 or you figured out. But if you want to measure current through a circuit, you've got to use your multimeter in current mode, right? We talked about using it in current mode and plugging in the 20 amp output so that you don't blow the digital multimeter. But if you want to measure the current, you got to measure the current through something, not across something. So to measure the current through something, you've got to break the circuit. So if I want to measure the current in this circuit, I want to measure the current coming out of the capacitor, right? I want to break the circuit, and then we can go, whoops, that's still an eraser. I want to break the circuit. Let's go to the digital multimeter in current mode and measure the current, right? So to measure the voltage, you just you can take your probes and you can put it across, or you take your alligator clips and you put it across the atom to measure the current. You got to break the circuit and measure the current through. Now, just to make sure we understand that I said we're going to measure the current from the capacitor, and so I measure the current there, but the current should be the same anywhere. I could break the circuit here. I don't know if you could see where I broke it. Okay, there. And put a current meter here, and the current should be the same anywhere because there's no branching here, right? There's nowhere for the current to go. The current through the resistor is the same as the current through the capacitor, is the same as the current coming from the battery. Now, you might ask, wait, what about these voltmeters? What about these voltmeters? Don't they take current? And the idea behind a voltmeter, an ideal meter does not impact your circuit. Ideal meters don't impact your circuits. Now, real meters do impact your circuits, and we might have to talk about that at some point. But ideally, the voltmeter doesn't pull any current. In reality, it pulls a little bit of current, but ideally, it doesn't pull any current, so it doesn't change the current in your circuit. You will see situations where the meters do impact your circuit, and so you got to be careful sometimes to pull your meter out of your circuit before you run it. Okay, so that's using meters, those are circuits. Oh, and then we talked about grounds, right? So we talked about the fact that the potential difference across your power supply is, or the potential difference being supplied by your power supply is just a difference between the bottom terminal and the top terminal. But those terminals themselves can be at a particular voltage. So if either of these power supplies were 9 volts, it's a 9-volt difference between the top and the bottom. It doesn't mean that the bottom is at 0 and the top is at 9, or the bottom is at 20 and the top is at 29. We don't know what the absolute value of the voltage is. So we want to put a ground in there, or we often want to put a ground in there. And so that ground pulls the bottom down to 0. So now that means that the potential difference here is the potential here is 0, and the potential here is 9. And with a variable power supply, that's actually going to vary. With an AC power supply, which the picture I'm drawing here, it will vary over time. But the maximum will be 0 to 9. Anyway, so the ground pulls the bottom down to 0, so that now we know that this is 0, this is 9. Okay. So grounds are something that sometimes we're concerned with, sometimes we're not. But one thing I want to point out is that once we add a ground to a circuit, there is a simplified way of drawing a circuit. And the simplified way of drawing the circuit is to not worry about the full loop, because we're going to go from the high voltage to 0. So we can simplify either of these circuits by drawing. This is my power supply. We call this, whoops, what happened there? We call that V, and then we go through a resistor, right? And we go through a capacitor, and then we go to ground. That is the simplified way of drawing the circuit. This picture right here is the same as either of the two pictures above without the meters. Right? We've got some kind of power supply. It goes through a resistor, through a capacitor, and to a ground. Now, in order to make a full loop, right, we could just go ahead and go, look, that's just going there, and there. That's the same circuit we had. But it's a simplified, right? So it's a really nice way of drawing circuits, a simplified way of drawing circuits. And this power supply here could be AC or DC in this case, because it's just drawn as a dot. Right, whoops, I didn't mean to put an arrow there. In these simplified circuit diagrams, we just draw the power supply as a dot, and we need to know whether it's AC or DC. DC we usually draw as 2 plates. AC we often draw like that. And by the way, you do sometimes see me drawing this, putting an arrow through the DC power supply, and that just means a variable DC power supply where we can turn the voltage up and down. But even if we don't draw the arrow through, we usually mean we can vary it, right? We can change that voltage. But in reality, I guess the 2 plates by themselves you would think is a fixed voltage. With the arrow, we can vary the voltage, and then the one on the bottom, the AC, where the voltage varies with time. But you want to get used to reading these circuit diagrams. You need to be able to, in your head, figure out that you start, for example. We're going to start with hooking up a power supply. Then we're going to put a wire to a resistor. Then we're going to put a wire to a capacitor. Then we're going to put a wire all the way back to the power supply, but that's going to be the ground side where we attach it to ground. And this is where on your power supplies, you have got three inputs, right? On the more complicated power supplies than those little black ones or than a battery. You've got those three inputs. I think they're usually green. I can't actually remember because I don't have it in front of me, but is it green, black, and red? Whoops, and red, right? You've got your three outputs, not inputs, your three outputs from your power supply. I think it's often green, black, and red, and the black is the negative, the red is the positive, and the green is the ground. The green is the ground. I drew an arrow there. Hold on, let me fix this. Okay, so this is your power supply output. You got a negative, a positive, and a ground, and we can literally go from, I didn't leave myself space, so you'll have to excuse me for writing on, oh wait, let me just start again. So you'll literally take a wire from the plus, you'll go to your resistor, you'll go to, and this is just an RC circuit with a resistor and a capacitor, and then you'll go to the minus, right? So you'll do that. But if you want to ground it, what you then do is you need to attach a wire between there, and now we've grounded the circuit and made the low side, the minus side. Oh, I did that wrong. Wait a second. I got that wrong, right? The black is always listed as negative and the red is positive. Sorry about that. So I fixed it. So the power supply, the black is always listed as negative and the red is as positive. Okay, so what I just did is I grounded the plus side, which isn't wrong. I can ground the plus side. So if I set this power supply at 9 volts, that now makes the high 0 volts and the low minus 9 volts. That's okay. It still works. But instead of being 0 volts to 9 volts, it's negative 9 volts to 0 volts. If instead I erased this black line here and I put a wire between green and black, okay, and don't worry about the fact that I kind of erased my inputs there, outputs there, I mean, then what's going to happen is now this one's set at 0 volts, and now this one's going to be plus 9 volts. Again, if the whole thing is 9 volts. So you can ground either side, and we will actually find where we want to sometimes ground the plus in order to make our voltages negative, or ground the negative in order to make all our voltages positive. In general, we're going to do it the way shown right here. So if you ground the negative, then all the voltages are higher than 0 throughout the circuit. Okay, and remember that this is the same as drawing this voltage to resistor to capacitor to ground. Where this is 9 volts and this is 0 volts going down. And the current goes in that direction. Current goes in that direction. From higher potential to lower potential. Current always travels from higher potential to lower potential. So if we changed this to negative 9 volts and this to 0 volts, then the current would actually go in the other direction. Because it always goes from higher to lower potential. So we could make the current go in the other direction by grounding the other output of the power supply. Okay, that's all I've got for the bridge from DC to AC, and now you'll get the AC. We'll talk about the AC circuits.